Ready? Alright, good afternoon everyone. My name is Michael Spain and today I'll be presenting my honours work which is titled Analysing the Impact of Increased Demand in Performance Limited Blockchains. So just before I get into the talk, I'd like to acknowledge the help of my supervisor, Vincent Cremoli, and my associate supervisor, Sean Foley, for their support and guidance throughout the year. I'd also like to acknowledge the Capital Markets Cooperative Research Centre for sponsoring this work. Okay, so a little bit of an introduction. So in 2008, the blockchain era began with the introduction of Bitcoin. Arguably, it was Nakamoto's proof of work process that enabled Bitcoin to become so successful. Since then, the underlying blockchain functionality has been significantly improved and extended. And in 2015, Ethereum generalized the blockchain paradigm. We now have several blockchains that are capable of performing arbitrarily complex computation. Now, as a result of this, demand has significantly increased in the commercial and public sectors for blockchain technology. However, the proof of work system that underpins these types of blockchains still has very limited performance. So, in this presentation, we explore the implications of that on miners and users, which are the two main types of participants in a blockchain. So a little bit of background before we get into the research motivation and the contribution. The goal of a blockchain is to provide a decentralized, secure record of transactions between its users. So in order to achieve decentralization, blockchains are structured in peer-to-peer networks. Right? Anyone can join or leave the process of validating and adding to the blockchain. It's known as mining. This structure means that the blockchain avoids having a single point of failure or control. Now, in order to achieve security, in proof-of-work systems at least, this relies on a combination of cryptography, economic incentives and penalties, and also a probabilistic solution for reaching consensus. So we're going to talk a little bit about proof-of-work now to understand what it is and what limitations it has. So in proof-of-work systems, the only way to append a block to the blockchain is by mining, which involves solving some sort of crypto puzzle, which is usually repetitively performing some hashing algorithm until you achieve a certain target threshold. Now, the properties of these hashing algorithms allow the network to control the rate at which blocks are added on average to the blockchain. So this is important as it helps deal with the inevitable message delays in distributed systems. Additionally, because this process costs both time and money, it provides an economic disincentive for people who want to be malicious and try and be dishonest in mining. On the other hand, though, people who find valid blocks that are added to the blockchain are economically rewarded in the form of some fixed amount of digital token, Bitcoin, Ether or something, and usually as well a sum of transaction fees from the transactions that they included. Okay, so the mining process allows the network to control the average rate at which blocks are added to the chain. However, there is still no guarantee how long a block, when it's found, will take to propagate throughout the network. And indeed, this time is constantly changing as nodes join the network and leave the network, and the delays between them always change. So as a result, there's going to be situations like this all the time, which are known as forks. And a fork refers to a situation when you've got one set of nodes that hear of a valid block B1, and another set of nodes that hear of another valid block B2 that both have the same depth in the blockchain. Now this is a problem because this represents two inconsistent versions of the global state. There are now two transient blockchains and we need a consensus mechanism to reach one true global state. So in proof-of-work blockchains, this is usually done by prioritizing the blockchain with the most hash power behind it. The rationale for this idea is that as long as the majority of hash power in the network remains honest, they will, with very high probability, generate the longest blockchain over time. So proof of work, in general, there are exceptions to this, makes the blockchain secure with to attackers with less than 50% of the hash power. For an attacker to modify some previous block in the chain, they need to recompute the proof of work for that block and all subsequent blocks that follow, because each block includes a reference to the previous block. This is only possible if they are able to generate blocks at a rate faster than the rest of the network combined. Okay, so proof of work allows us to define throughput and performance in the blockchain in terms of two parameters: the number of transactions in a block and the block interval, which is how frequently the blocks come out. So research has shown that trying to increase throughput by either increasing the number of transactions in a block or by decreasing the block interval inevitably leads to more forks in the blockchain. This is because of the message delays we have in this type of system. So in addition, forks, in addition to actually representing inconsistent states, global states, they also represent a system or a situation where security has been diminished because now the honest power of hash nodes that are not malicious is divided into separate blockchains. So to combat this, blockchains set a maximum number of transactions that can be included in a block and try and target a constant block interval in order to maintain some security threshold. This is why proof-of-work blockchains have such low maximum throughput compared to traditional centralized systems. Here we see a little comparison of Bitcoin and Ethereum can do roughly around 10 and 20 transactions per second compared to something like Visa, which can do a maximum of around 50,000 transactions a second. So, proof of work has made the blockchain successful, but at the expense of high performance. Now, why is this an issue? In 2017, demand for blockchains has increased significantly in the commercial and public sectors. This graph here shows the number of transactions recorded per day in Ethereum, which is one of the world's largest blockchains. We can see that towards the start of the year, it was around 50,000 transactions per day, and up to recent times, we've seen over 500,000 transactions per day, a very, very significant increase. So what is the problem statement we're trying to address in this work? Well, we've seen how proof of work inherently limits the performance of the blockchain and how demand is growing. So we want to understand what is the impact of this increased demand in a performance-limited environment, that is the proof of work environment. We want to consider the two major groups of users in a blockchain, the miners and the actual users that send transactions. So my contribution I'll be discussing today is threefold. First, I explore the mining environment under a period of high demand to understand how that's affected by increased demand. We then conducted an empirical study to work out transaction latency and analyse those results to understand the significance of the transaction fee in determining latency. So, choosing a test blockchain. We chose Ethereum for these tests for several reasons. Ethereum is Turing complete. It has a generalised blockchain functionality, which means that and it's also quite high performance as well. So these two reasons have led to the significant increase in demand that I showed you in that graph. So it served as a perfect test for these sorts of experiments. So the Ethereum mining environment is our first contribution, and we wanted to understand the impact of increased demand on mining revenue and on mining costs. We looked at the Basic Attention Token Initial Coin Offering, BAT ICO, which represented a period of very, very high demand in Ethereum. We wanted to see how this ICO affected revenue and also performance in Ethereum. So the key results I'll show you today are fees per block, revenue, and gas used, which is a proxy for network performance. So this graph here is a logarithmic scale on the y-axis, and we can see that the BAT ICO caused a massive increase in the revenue in fees, that is, given to the miners per block. So the BAT blocks recorded an average of 28, 35, and 12 ETH over 3 blocks, as opposed to an average before and after 1 day plus or minus of about 0.08 ETH. This is hundreds of times larger than you'd usually expect. Massive, massive increase. So these findings show just how competitive some users really are at being able to transact at a specific time. Now, we wanted to understand, on the other side, what was the demand placed on the miners of these blocks? If they're getting hundreds of times more revenue, what is the demand placed on them, and what's the network performance like in general? So this graph shows the rolling average of gas used over the period, right? And we can see that during the BAT ICO, the rolling average of gas increased significantly to around 4.3 million, right in the middle at the top there. Now, this represents the maximum possible work that could have been done. The gas limit at the time was around 4.3 million. So this is the problem here, is that the number of transactions and therefore work is capped by the gas limit, which means the network cannot perform above this level. So while this is a significant increase of 1 to 2 times, it is completely insignificant to the transaction fees that were generated, which are hundreds of times larger. So, findings and motivation from this work. We know that proof of work limits the maximum achievable performance in Ethereum and generally in proof of work blockchains. However, we've seen that there is no limit on the transaction fees set by competitive users in this environment. The transaction fee is supposed to act as a mechanism to incentivize fast inclusion times. But having seen the impacts of increased demand on mining revenue and costs, we wanted to investigate this question from a different perspective. What impacts does demand have on the users in Ethereum? So, we conducted a study to determine transaction latency. We considered about 25 days or 3.5 weeks of Ethereum transaction data, representing about 6 million committed transactions. The key results I'll be presenting today are latency distribution, the fee distribution, and there's some demand versus supply regression as well. Okay, so Median latency throughout the study was around 22 seconds, which when considering the average block time was about 17.5, means that in general, Ethereum was committing transactions or including them within about 2 blocks, okay, which is pretty good. But when you look at the distribution of latency, the results become much more interesting. You see around the 90th percentile, the shape of the curve changes dramatically. There's a point of inflection. This posed an obvious question. We wanted to understand what was it about this outlier group of transactions that made them take so much longer to be included than the first 90%. So the first thing we did was we thought, let's compare the fee distributions between the fastest 90% and the outlier 10%. We know that because in blockchains, the fee is supposed to incentivize faster inclusion, it's supposed to incentivize the miner to include you. The hypothesis here was that maybe this group just paid either no fee or a very small fee, therefore miners neglected the transactions for as long as possible. So here, this table represents a comparison between the fastest 90%, the distribution of their fees, and the slowest 10%. And what we notice is not only are the distributions really similar, actually at points the slowest outlier 10% are paying more in comparison to the fastest 90%. So they're paying a similar fee, sometimes more, but receiving significantly or exponentially worse latency. Now, at first, these results seemed counterintuitive, so we began to investigate the performance limitations of Ethereum and proof of work. So, proof of work dictates a semi-constant supply. In Ethereum, this is determined by the gas limit. So, we took the average gas limit for the study, and we worked out that in essence, proof of work capped Ethereum to around 245 transactions per minute throughout our study. Now, if we look at this table, which is a distribution of demand in Ethereum, we looked at each minute and said how many transactions were issued in this minute. If we look at this distribution, we see the 90th percentile is around 244, almost exactly 245. Coming back now to our original graph, we understand why the shape starts to change so much at the 90th percentile. It's because this 10% represents times when Ethereum demand outstrips supply, and therefore the transaction fee fails to incentivize inclusion when demand outstrips supply. This creates an unfair and unequal environment for users. So we have these results now. We wanted to know if we could strengthen them by performing some sort of regression analysis and considering the impacts of high versus low demand and high versus low supply. So the aim of these regressions was to understand the statistical significance of network demand and supply in the fee versus latency relationship. So we consider a simple regression model where latency is inversely related to fee. The justification for this model is based off the properties of the data set. So there were no transactions committed in our study with a transaction fee of 0. We also know that it's impossible to achieve a latency of 0, so we can be pretty confident that our data is asymptotic both in the x and in the y-axis. So what we decided to do was split the data into subsets that represented high and low demand and high versus low supply. Now, the justification for the demand split is based on the analysis that I just showed before, which we worked out. Above 245 transactions per minute, there's a problem. Under 245 transactions, we think it'll be okay. On the other hand, high versus low supply, we did this by, luckily in our study, well not luckily, but fortunately in our study, we actually experienced one significant raise in the gas limit from 4.7 to 6.7 million. Now, this represents about a 40% increase in capacity, so it's very, very nice for us to be able to look before and after and say what is the difference of this change. So here we graph the fee coefficients gained from our regression analysis of the high versus low demand subsets. And we can see when demand is low, the relationship is more hyperbolic. When demand is high, it becomes less hyperbolic. This is representative of, so when the demand is low, the marginal reduction that can be gained per extra unit of fee is higher than when demand is high because there is more capacity for the network to commit transactions. Similarly, with the gas limit, something happens in the inverse. When the gas limit is high, the relationship becomes more hyperbolic. This is because capacity is higher, we can commit more transactions, therefore every extra unit of fee you pay will make more of a difference in your latency. Conversely, when the gas limit is low, you get less of a difference. Okay, so some conclusions. We've seen how proof of work essentially has a fixed supply, and we're sort of dealing with really, really rapidly increasing demand in blockchains. Situations where demand outstrips supply means that the transaction fee fails to provide fairness to users, and this is a problem. Future work. I believe that blockchain clients should help users become aware of sort of periods where demand exceeds supply to avoid them paying for performance that they're never ever going to be able to receive. I believe this is a problem with blockchains. Fundamentally, though, this is a problem with the proof of work process, and there's a significant amount of work being done right here at the university with the Red Belly blockchain and different approaches to consensus. Thank you.
So I guess first is your first experiments were on this ICO.
Yep. Yep.
It was 3 blocks. Is that normal? That's so short?
So some of the ICOs have, like, they sort of changed it as a consequence of these kind of ICOs because they realised this was like a massive denial of service on the network. But the BAT one was, where is it? Yeah, two further back. Yeah, so the BAT ICO was 3 blocks. I think it was, I haven't actually labelled it there, sorry, but it was 3 blocks. The first one was recorded fees of 28 ETH, the second one 35, and the third one 12. And then the results are taking, the rest of the sample is a day plus or minus to get an idea of average conditions at the time.
Do you think you see similar jumps in longer running ICOs?
Not as much, no, because it allows, I think people start to understand that because there is this fixed supply in Ethereum and proof of work in general, if you have this short, tiny sort of, everyone in now or you're not going to get in at all, it sort of causes these sort of effects. But at the same time, there's a problem for ICOs because they can't really go on indefinitely because then people have no certainty of valuation that they're buying in at, right? So there's a sort of, it's a bit of a dilemma.
And also about this jumping gas limit,
Mm.
do you know, is there, so you said
Yeah.
there's been thought on that?
Yeah, so in Ethereum, sorry, I should have explained this, the gas limit is determined every time a block is found. The miner has a vote whether or not they want to increase the gas limit, decrease it, or keep it the same. So our study started on the 24th of June, it went through to the 17th of July. On the 29th of June, the miners sort of coordinated and consistently voted up the gas limit over a period of about 12 hours, and that was to alleviate congestion that had been caused by some of the largest ICOs, which were Status and Bancor, that had happened sort of 2 or 3 weeks before. So that allowed us to look at this increased capacity and say, okay, well, what is the difference in the fee latency relationship before and after?
So the community decided.
Essentially, yeah, it was just they sort of bowed to pressure from the Ethereum Foundation that they should probably do something about it and actually increase the gas limit.
And is there,
It can go up infinitely. It's sort of set so that it should, in theory, in a just sort of environment, it should reflect the capabilities of the miners. But obviously with centralisation of mining and stuff like that and mining pools, they sort of have a monopoly over what it can be. So that was a problem, is that for ages Ethereum was having full blocks and heaps of pending transactions, but the miners just wouldn't vote the gas limit up. So yeah, it was a bit of an issue.
I guess last question is, can you correlate any of these results to existing supply and demand models?
Yeah, you probably could. I haven't done that actually, but yeah, I could probably look at. Yeah, I mean, essentially, like you said, it's looking at essentially what is a fixed supply line versus a variable demand line. So I could probably try and apply more traditional economic models. Yeah.
So you looked at or you showed that the increase in, the slowest 10% had a significant, or often had an increase or larger fee than the remaining 9%. Seems like this is going to be a period of really high demand, right? So I wonder if you looked at the periods where you had the fastest, rather than comparing the slowest 10% to the other 90%.
Yeah.
If you could compare the fastest 10% with the slowest 10%.
I know we spoke about this, and I did look at the fastest 10, the middle 80, and they actually were consistent with what I've showed there. So it wasn't like sort of just, those results weren't sort of skewed by the first 10% sort of moving the average of the top 90. They're actually quite consistent across the board. So that was interesting, but yeah, probably.
And I wonder if this could be kind of extended to other blockchains where you have things like forks that significantly change the throughput at the same point in time.
Definitely, I think, and I mean, what this really is an evaluation of proof of work in the Ethereum context, but it can be applied to proof of work blockchains generally. So Bitcoin, I chose Ethereum because I think, one, Ethereum's probably had more of a demand increase this year than probably any other blockchain, which makes the experiments more interesting, makes the limits more tested, but it could be applied to Bitcoin, it could be applied to other proof of work blockchains. So yeah, I think that would be interesting to do, to look at the impacts or similar sort of analysis performed in different environments. Thank you.
Even our first one started late, but the market forgot that it needs to come.
Has there ever been a case where the examiner doesn't come?
Well, that's why we record it, just in case that if someone has already told, yeah, that's recorded. Yeah, 2 years yesterday. I mean, so you can. I'm trying to put the video up if you want to see yourself and then cut the one that you like as your honors, memorable, something like that. Oh, why not? Yes. Yeah. We can see how you sort of like running around on the stage and yeah. That's good. Yes. And then we can how many that you have to like what left and right. Yeah. Yes. So we're recording it. That's why that's. Yeah. I feel Mark is actually indicated that they were actually away and they're going to come.
So what do you do? Do you do like it?
No, that ain't mine.
Did you just relax it?
I just have to stand by. Well, your kid said that he's taking notes. I'm also taking notes, just in case that sometimes some arguments or some things like they want to be